If you enjoyed this podcast, please consider liking, sharing, and subscribing to the channel. The paradox emerges. Scientists discovered something very strange when they looked closely at their own equations. In the late 1600s, Isaac Newton wrote down the laws that govern how objects move. When mathematicians studied these equations, they found something puzzling. The math worked exactly the same, whether time moved forward or backward. Picture a planet going around the sun. Newton's equations describe this motion perfectly. But here's the odd part. If you ran the math in reverse, the planet would trace the same path backward through space. The equations couldn't tell the difference between forward time and backward time. This seemed fine until scientists compared their equations to real life. A hot coffee cup always cools down. It never gets hotter by itself. A broken glass never jumps back together. Gas from a punctured balloon spreads out but never gathers back inside. Every single process in the real world has a clear direction in time. How could the fundamental laws of physics work both ways while everything we see only works one way? This question would haunt physicists for centuries and still puzzles them today. The Entropy Enigma. The second law of thermodynamics appears to solve our mystery. It states that entropy, the number of ways particles can arrange themselves, always increases in isolated systems. When you drop ink into water, millions more arrangements exist for mixed ink than for separated ink. The system naturally moves toward the more probable state with higher entropy. But this mathematical rule only describes what happens. It doesn't explain why time flows in one direction. The underlying physics equations work perfectly when run backward. Every collision between molecules could theoretically reverse itself. Yet we never see mixed ink spontaneously separate back into a droplet. Austrian physicist Ludwig Boltzmann faced this puzzle in the 1870s. His student, Johann Loschmidt, pointed out a troubling fact. If the microscopic laws are reversible, how can the macroscopic world be irreversible? Later, Ernst Zermelo noted that any finite system must eventually return to its starting state, contradicting permanent entropy increase. These challenges reveal a deeper problem. The second law might simply reflect special conditions at the universe's beginning, rather than fundamental physics. Why did our cosmos start in such an organized, low-entropy state? The universe's mysterious beginning. Scientists have found something deeply puzzling about our universe's earliest moments. The official records from space telescopes and cosmic measurements show that the universe began in what physicists call an extremely low-entropy state. This means everything was incredibly smooth and organized, not the chaotic mess you might expect from a random explosion. Think of it this way. Imagine shaking a box of puzzle pieces. You would expect them to scatter randomly everywhere. But according to documented observations, our universe started more like those puzzle pieces were already neatly arranged in perfect rows. The cosmic microwave background radiation shows this smooth beginning, with temperature variations of only 1 part in 100,000 across the entire observable universe. This creates a major problem for scientists. Mathematical calculations show that if you randomly picked a starting point for the universe from all possible arrangements, you would almost certainly get a lumpy, chaotic mess filled with black holes and dense clumps of matter. The probability of getting our smooth, organized beginning is so small that it's like winning every lottery on Earth simultaneously for 1 billion years straight. How could the universe have started in such an incredibly special state? This question challenges everything we think we know about cosmic origins. Cracks in perfect symmetry. Scientists discovered something strange in 1964 that shook our understanding of time itself. James Cronin and Val Fitch observed neutral kaons, tiny particles that exist for mere fractions of a second, behaving differently when their decay processes were reversed. These particles seem to prefer one direction of time over another, even at the smallest scales imaginable. The discovery earned them a Nobel Prize and opened a crack in what physicists had assumed was perfect symmetry. The violation appeared in what scientists call CP symmetry, a combination of charge conjugation and parity. When researchers applied the CPT theorem, which links charge, parity, and time reversal, they realized something profound. If CP was broken, then time reversal symmetry had to be violated too. This meant certain particle interactions actually distinguished between forward and backward time directions, independent of any thermodynamic effects. Later experiments with B mesons confirmed these findings. Specific decay pathways showed clear preferences for particular time orientations. The question became whether these microscopic violations could explain our everyday experience of time's arrow. Could such tiny effects in obscure particles really determine why we remember the past but not the future? The mathematics suggested otherwise. These violations seemed far too weak and specialized to influence macroscopic processes. The observer's dilemma. Consider this simple fact about your daily experience. You remember eating breakfast this morning, but you cannot remember what you will have for dinner tomorrow night. This basic truth of human consciousness reveals something profound about time's direction that goes far beyond physics equations. When neuroscientists study memory formation in the brain, they find something remarkable. Every time you create a lasting memory, your neurons must use energy to build new protein structures and strengthen connections between brain cells. This process always increases entropy in your brain tissue, generating heat and using up chemical energy that can never be perfectly recovered. Your ability to remember the past literally depends on the same thermodynamic arrow that makes ice cubes melt and coffee grow cold. Laboratory studies show that forming memories requires about 20 watts of continuous power in the average human brain. This energy consumption creates irreversible changes in neural pathways, leaving permanent traces of past events. Yet somehow, despite using the same physical brain, you cannot form memories of future events that have not yet occurred. Brain imaging reveals that when people think about past events versus future possibilities, different neural networks activate in distinct patterns. The past triggers specific memory centers, while imagining the future engages planning and creativity regions. This suggests our brains have evolved specialized mechanisms that treat yesterday and tomorrow as fundamentally different categories of experience. The unresolved question. Scientists have developed three main ways to explain why time moves forward instead of backward. Each approach tackles the problem from a different angle, but none provides a complete answer. The first explanation points to the universe's starting conditions. According to this view, our universe began in an extremely ordered state with very low entropy. This special beginning set up the conditions for time's arrow. However, this raises troubling questions. Why would the universe start in such a perfectly organized way? The odds seem impossibly small, suggesting our explanation might be missing something important. The second approach looks for built-in differences in the laws of physics themselves. Some experiments show tiny violations in how particles behave when time runs backward. But these violations appear far too weak to explain the strong direction we observe in everyday life. A coffee cup still won't spontaneously reassemble from its fragments, even with these microscopic effects. The third strategy claims time's direction emerges from how we observe and measure things. When we look at large systems, we naturally focus on certain features while ignoring others. This coarse-grained view, combined with quantum effects and our memory formation, might create the appearance of directed time. Critics argue this doesn't solve the mystery, but simply pushes it to a different level.